Welcome to an exciting conclusion to this course. As we have previously seen, this thing called L'Hopital's rule can help us evaluate limits. Uh, if the limits are in the form 0 divided by 0 or infinity divided by infinity, two of our basic indeterminate forms. But there are other indeterminate forms. So this is going to get a little bit more involved. So part of it is recognizing those indeterminate forms and then looking at the technique of how to change it to 0 divided by 0 or infinity divided by infinity. Because that's still the only way we can apply L'Hopital's rule. So let's look at this first one. If I try to put infinity in, square root of infinity is infinity. 1 over e to the infinity is going to be basically, that's going to be 0. So this indeterminate form is 0 times infinity. We have a function getting really small multiplied by a function getting really large. So which one wins? Well, what we need to do is, it's probably the simplest one to adjust, is to change it to a quotient. So changing this to a quotient doesn't take a lot. I will first write this as the limit of radical x over e to the x as x goes to infinity. Now I can look at it and see it as infinity divided by infinity. So now if I go ahead and apply L'Hopital's rule, this is going to be 1 over 2 radical x divided by e to the x. And that still looks a little funny, but from here to here I applied L'Hopital's rule. Now I'm just going to change it algebraically. It becomes 1 over 2 radical x e to the x. Well, if I put infinity for both of these, this number's getting huge. That's just 1 over infinity, so I get 0. All right, but at the beginning, I didn't really know what's happening because it was this indeterminate form. Second indeterminate form is a function where if I put infinity in for x, I get 1 over infinity, which is 0. This whole thing becomes 1 to the infinite power. Now, we might think that the number 1 to any power is 1, which is true. But this isn't a number 1. It's a function getting close to 1. But I'm raising it to a really big power. So is it getting very large? Is it getting very small? Or is it becoming some other number? This one, along with our next example, involves an exponent. So what we're going to have to do is make use of something similar to what we called logarithmic differentiation. So here's the process. I'm going to let this whole thing be an expression. I'll call it y. So I'm going to let y equal this limit. Again, this is a technique we're going to use whenever we have an exponent that's a variable. Now, we don't typically like to work with exponents, and the properties of logarithms are going to save us. I will now find the log of both sides. That's the log of y equals the log of all of this. Now, there are several properties of limits, and one of them is that if I take the limit of something and the log, I could have taken the log first and then the limit. So through a few steps, what I can basically write algebraically is this thing is going to be the limit of, if I take the log of all of this expression, I can bring the x to the coefficient spot. Right, so taking the log of this expression becomes this part in brackets, and I'm still taking the limit as x goes to infinity. Now we're still not sure what's happening. If I put infinity in, this becomes infinity. If I put infinity here, we get the log of 1, which is 0. Oh, so now we're back to this one. We have infinity times 0. And the way I deal with that is to make it a quotient. So I'll take the log of y equals the limit as x goes to infinity. I'll make it the log of 1 plus 1 over x divided by 1 over x. Instead of multiplying by x, I can divide by 1 over x. Now if I try direct substitution, 1 over infinity is 0. Log of 1 plus 1 over infinity is also going to be 0. I finally have a situation where I can apply L'Hopital's rule. So I end up with the log of y. The derivative of the top is 1 over all of that. It's going to look complicated. Times the derivative of what's inside. And the derivative of 1 over x is going to be negative 1 over x squared, divided by the derivative of the bottom, which is also negative 1 over x squared. Well, now to complete it, I need to take the limit of that, sorry. Taking the limit of this whole mess. But we can still use algebraic techniques. These cancel. So I'm really taking the limit of 1 over 1 plus 1 over x as x goes to infinity. So I put infinity here. That's going to be 1 over 1 plus 0, so I get 1. Now, this limit is not 1. Remember, the log of y equals 1. So if the log of y equals 1, y must be the base to the first power, which is e. So this thing is e. That mysterious number, irrational number, famous number, is going to be e. Now, that was a lot of work. Let's take a look at another example that's similar because we have an exponent. And I may not carry this one all the way through. I may let you finish it on your own. But let's take a look at what indeterminate form it may be. If I put a 0 in, I'm only going from the positive side, so I don't either have the negative or the positive. The sign of 0 is 0, but I raise it to the 0 power. Now again, this may not look like an indeterminate form. But as we get a number closer to 0, and if I take a power that's a root, like a 1/2 or a 1/3 or a 1/4, you take a root of a number between 0 and 1, it actually gets bigger. Just look at something like the square root of 0.81 is actually 0.9. So you got a number getting smaller, closer to 0, but you're taking a really small root, the number should be getting bigger. We have a contradiction here, so it's an indeterminate form. But I'm going to use the same technique. I'm going to let y equal that whole expression. Now I will take the log of both sides. And doing that, it's going to allow me to write the limit as x goes to 0. That x can be now put in front of the log. Let's think about what we have. If I put a 0 in, this now becomes 0. If I put a 0 in here, it's sine of 0, 0. Log of 0 is basically infinity. It's really negative infinity, but that's the same idea. We're back to that term, so we have to make it a quotient. Take the limit as x goes to 0 of the log of sine of x divided by 1 over x. I'm now going to use L'Hopital's rule. The derivative of this is 1 over sine times cosine. The derivative of 1 over x is negative 1 over x squared. So now as we look at it, this is basically going to be 1 divided by 0, which is infinity. And now this is infinity. So we still have an indeterminate form. And this is where I'm not going to finish it, because what we would need to do is just apply L'Hopital's rule again. Maybe make this cotangent. Find the derivative of cotangent, derivative of this, and it is an example in the text you could study, but I'll let you kind of finish that. But the idea is that whenever we have these exponents, we need to use this logarithmic process. Last one. Okay, the limit of 1 over log x, 1 over x minus 1 as x goes to 1. We put a 1 in here, that's 0, so we get infinity. We put a 1 in here, that's 0, so we get infinity. And I think I may have talked to you about this before, that infinity minus infinity we might think is 0, but again it's an indeterminate form. One might be getting much larger than the other one. So this could be 0, it could be infinity, it could be 1/2, who knows. But our big problem is, how do we handle this? How do we make this a quotient so we can apply L'Hopital's rule? Well, it's pretty much algebra. We're just going to have to get common denominators and make it one expression. So, if I do that, I'm going to have the limit as x goes to 1. If I get common denominators here, this one would have to be multiplied top and bottom by log x. This one would have to be multiplied top and bottom by x minus 1. So we're going to have the expression x minus 1 minus log x all over log x times x minus 1. Now, let's see what we got. If we go ahead and put a 1 in, we got 1 minus 1, which is 0, minus log 1, which is 0, so we have 0. We put a 1 in here, log of 1 is 0, 0, we get 0, so we're good. We can apply L'Hopital's rule exactly as this stands. When we do so, we have the derivative of the top, which is 1 minus 1 over x. Derivative of 1 is 0. On the bottom here, we're going to need a product rule. Derivative of log x is 1 over x times that second term plus the derivative of the second term, which is just 1, times log x. Now, let's see what happens if we try to put a 1 in. The top, we have 1 minus 1 over x, which is 1, so that's still 0. The bottom, we get 0. We still get 0. So this is a case that we might want to play with it a little bit and simplify it and rewrite it. We could use L'Hopital's rule right away, but I'm not going to. One thing I can maybe see is I'm going to multiply top and bottom by x. I just don't like the fraction within the fraction. So we do have an algebraic step. We multiply top and bottom by the x. I get x minus 1 divided by, if I multiply all of this thing by x, I'm going to get x minus 1 plus x log x. Now that should still be 0 over 0 if we try to plug the 1 in. But now at this point, I can go ahead and use L'Hopital's rule again. Derivative of x minus 1 is 1. Derivative of this x is 1. That's 0. Here I have a product rule. Derivative of the first is 1 times the second, plus the derivative of the second, which is 1 over x times the first. If we simplify that, we get the limit as x goes to 1. 1 over, that's still 1, get log x, plus 1. Log of 1 is 0, get 1 over 2. So you can walk out of the day thinking, whoa, infinity minus infinity is 1/2. Only if the two functions that lead to that infinity are these two. Okay, as I said, it got a lot more involved. Good luck with this. Please let me know if you have any questions or problems, and we'll take care of those with the solution video. Look for more early next week. And congratulations, we've made it.